So let's look at one more example problem of these exponential model word problems where this one's a little bit more difficult. It has one extra step compared to our first introduction problem. And I'll probably pronounce this name wrong, but let's say Katya is a ranger at a nature reserve in Siberia, Russia, where she studies the changes in the reserve's bear population over time. The relationship between the elapsed time t in years since the beginning of the study and the bear population, which is b of t, on the reserve is modeled by the following function. So we have this equation here. In how many years will the reserve's bear population be 2,000? So we'll need an approximate answer here. We need to round it, if needed, to the nearest hundredth. And we're looking at how many years it'll take. So like all of these problems, we want to start by defining what the variables represent. So we need b of t and we need t. And t, like our previous example problems, will be time. And again, we're looking at a unit of years. And b of t in this case is the bear population. So b for bears. And the unit for this is just the number of bears. So we are told that the bears population will be 2,000 bears. And we need to figure out in how many years that will take place. Since notice the unit of our answer here. So b of t, we're told the number of bears is 2,000. And we can even say 2,000 bears. And we need to figure out how many years that will take. So we're going to set b of t equal to 2,000 and then solve for the variable t here. So let's just rewrite that with 2,000 bears put into the equation. So we have 2,000 is 5,000 multiplied by 2 raised to the minus 0.05 times t. And we just need to solve for t. So the strategy for these, remember, is to solve for the exponential term. And then from there, we can rewrite it as a logarithm. So we'll divide each side by 5,000. So 2,000 divided by 5,000, we can simplify that to 2/5. And now that we've solved for the exponential term, we can rewrite it as a logarithm. Since remember, if you have some exponential equation, let's say we have a to the b is equal to c, then you can rewrite this as a logarithm where the logarithm will have the same base. So it'll be log base a, and the logarithm is equal to the exponent. So the logarithm of our input is equal to b, and the input of the logarithm is what the exponential equation is equal to. So this would be log base a of c is equal to b. But the best way to remember this is that they have the same base, and to remember that logarithms are exponents. So the logarithm will be equal to whatever your exponent was up here. Now, rewriting this as a logarithm, we have log base 2, since the base of our exponential equation is 2, of 2/5. Since remember the exponential equation is equal to the input of the logarithm. And the logarithm, of course, is going to be equal to our exponent here. So minus 0.05 times t. And we need to solve this for t. So we'll have to divide each side by this minus 0.05. So if we do that, we have log base 2 of 2/5 divided by minus 0.05, and this is equal to t. So this is our exact answer, but we need to come up with a decimal answer that we can round. So we need to use a calculator at this point. And some graphing calculators do have the ability to put in custom logarithms, but many of them don't. And if your calculator doesn't have that ability, you'll need to use what is called the change of base rule. So let me just make a little bit of room for that. And remember, the change of base rule essentially will allow us to take any base of a logarithm. So let's say we have log base m of n, and we can rewrite this with any new base we want. So let's say we want to rewrite it with base d. So this could be equal to log base d of n divided by log base d of m. And this is very general, but it'll make more sense with an example. So notice that we get a quotient where you have two logarithms, and the base of each of these new logarithms is base d, whatever you want it to be. And usually you're going to change it to base 10 or base e, since many calculators will have those as buttons you can use. And the numerator of our quotient here will have its input be the original input of your logarithm that you started with. And the denominator will have as an input the base of the original logarithm. So with our example here, or with our specific problem, we have log base 2 of 2/5, and we can use log base 10. So we'll say that this is now a quotient where we have log base 10 in the top and the bottom, and in the top the input will be the original input. So we'll have 2/5, and in the bottom it will be the original base as the input. And remember, a log base 10, that's just the common log. So the button on the calculator is just log, where the base is implied to be 10. So you have log of 2/5 divided by log of 2. And we could also use the natural log, since we often have that button as well if we have the common log button. So we could write this as the natural log of 2/5 divided by the natural log of 2. And if you plug both these into the calculator, you will see that you do get back the exact same number. So we'll have to use this rule here. And like I said, let's just use the common log. So this will be equal to log base 10 of 2/5 divided by log base 10 of 2. And then we'll divide all of that by minus 0.05. And we're going to approximate the answer and round it to the hundredths place. So after plugging this into your calculator, you should get 26.4385. But if we round it to the hundredths place, we get 26.44. And the unit for this is years, since we were finding the time value. So if we go back to our original problem, we can put 26.44 into our box, though we can also check this problem. So let's make a little bit of room and try to do that. So if we check, we're essentially going to plug into our equation this t value of 26.44. And we need to be a little bit careful, because when we plug that in, we're not going to get exactly 2,000 bears, since this is approximate, but we will get roughly 2,000. So if we plug in to our function b, this 26.44, that will now be equal to 5,000 multiplied by 2 to the minus 0.05 multiplied by 26.44. And if we plug this into our calculator, we will get 1,999.90 bears. So, of course, this is very close to 2,000, so we can feel confident that this is roughly the exact amount of time it'll take for the population to reach exactly 2,000.